Hey, welcome. Every single time you buy something online, book a flight, or heck, even just like a photo, you're tapping into this secret world. A world with invisible rules that stop the entire internet from collapsing into total chaos. So today we're going to pull back that curtain and see what's really going on. Let's get into it.
So let me ask you this. Picture it. Your favorite band just announced a tour. You're waiting, you're ready, that countdown timer hits 0, you smash the buy button on the very last ticket. The little wheel spins, and you got it. But have you ever just stopped and wondered, really think about it. In that one tiny fraction of a second, hundreds, maybe thousands of other people are all clicking the exact same button. So how on earth does the system know to give that ticket to you and tell everybody else sorry, you were just a millisecond too late?
Well, that whole crazy scenario is what we call the digital race. Or if you want to get technical, a concurrency problem. It's the massive challenge of managing tons of people all trying to access and change the exact same piece of data at the exact same time. Now, the solution isn't some kind of dark magic. It's actually a really elegant concept in computer science that basically acts like a traffic cop for all this digital information. It makes sure every single interaction happens in a way that's fair, orderly, and, most importantly, reliable. And the hero of our story today? It's called the transaction. Yeah, I know, simple name, but it's an incredibly powerful idea that is the foundation for almost everything we do in the digital world.
So what is a transaction? Well, it's not just one thing happening. It's a whole sequence of operations that are all bundled together. The system treats this entire bundle as one single indivisible thing. And the rule is dead simple. Either every single step in that sequence succeeds, or none of them do. There is absolutely no in-between.
And booking a flight is the perfect example. You think it's just one click, right? Nah. Behind the scenes, the system has to check for available seats. Then it has to reduce the seat count by 1. And then it has to create your reservation record. If any of those steps fail, like if the system discovers there are actually 0 seats right after you started, the whole thing gets a rollback. It's like hitting a giant undo button. The system just pretends none of it ever happened. Only if every single step succeeds does it finally commit.
Okay, so to make sure every one of these transactions is completely trustworthy, it has to follow a really strict set of rules. You can think of it as a code of conduct for data, and it's known by a super cool acronym, ACID.
We've actually already been talking about the first and maybe the most important rule. A is for atomic.
Exactly like an atom was once thought to be something you couldn't split, a transaction is an indivisible unit of work. This is what prevents those nightmare situations, like money leaving your bank account for a transfer that never actually shows up on the other end. It either works completely or it rolls back completely. All or nothing. Simple as that.
The rest of the letters in ACII just build on that all-or-nothing foundation. C is for consistency, which makes sure the database doesn't break its own rules. Like a bank account can't have a negative balance. If a transaction tries to do that, it just gets rejected. I is for isolation, and that solves our concert ticket problem. It builds a little wall around each transaction so two people can't mess with each other's purchase. And finally, D is for durability. That means once your transaction is committed, once you get that ticket, it's permanent. It's written to the hard drive, and it's going to survive a power outage or a crash. What's done is done.
So ACID properties are basically the good guys, the guardians. But what happens if we don't have them? Who are the villains they protect us from? This is where we get to see the chaos that happens when that digital race gets completely out of control. So there are 3 main bad guys in this world of data. You've got lost updates, which is, exactly what it sounds like. Then there's uncommitted data, which is when one process reads information that another process ends up canceling. And finally, inconsistent retrievals, which gives you reports and numbers that are just flat out wrong. To really get why this is so bad, let's zoom in on the most common villain of them all, the lost update. Imagine 2 different people, or 2 automated systems, trying to buy an item from the same online store at pretty much the same time. All right, let's watch this train wreck happen in slow motion. At time 1, transaction A reads the stock level and sees there are 10 items. A split second later, transaction B does the exact same thing, and it also sees 10 items because nothing's been saved yet. Now they both go off to do their math. Transaction A says, okay, 10 minus the 2 I'm buying, that leaves 8. Transaction B says, 10 minus the 1 I'm buying leaves 9. But here's where it all goes wrong. At time 5, transaction A saves its result. The stock is now 8. But at time 6, transaction B, totally clueless about what just happened, saves its result
And now, the final stock level is 9. Transaction A's purchase of 2 items, it's gone, vanished, completely overwritten like it never even happened. That is a lost update. The store just lost 2 items, the database is wrong, and everything is a mess. This is precisely the kind of chaos that transaction isolation is built to prevent.
So how do we stop this from happening? How does that isolation part of ACID actually work its magic in the real world? Well, the main tool in the toolbox is something called locking.
A lock is basically a digital do not disturb sign. A transaction slaps this sign on a piece of data it's working on, and while that sign is up, any other transaction that comes along just has to wait in line. This prevents them from reading or writing data that's in the middle of being changed.
And they come in 2 main flavors. You've got a shared lock, which is for reading. Think of it like a book in a library. A bunch of people can all read it at the same time. But then you have an exclusive lock for writing. That's like checking the book out. Once you have an exclusive lock, nobody else can even look at that data, let alone change it, until you are completely done.
Now, to manage all this, databases use a really strict strategy called 2-phase locking. In phase 1, the growing phase, a transaction is like a shopper going through a store, grabbing all the locks it needs for its items. It can't let go of any of them. Once it has every single lock, it does its work. Then comes phase 2, the shrinking phase, where it releases all its locks at once. This strict collect-then-release process guarantees that the end result is the same as if all the transactions had just happened one by one, in a nice, neat, orderly line.
So we've got these incredible rules, transactions, ACID, locking. It's a whole system. But who actually sets all this up? Who are the guardians making sure all these systems are running the way they're supposed to?
Well, that job falls to a real person called the Database Administrator, or DBA. They are the human guardians who configure these rules, who set up the security, who manage the integrity, and who plan for disasters to make sure this whole complex dance works perfectly.
And the DBA's ultimate weapon is something called the transaction log. This is the D in ACID, durability, brought to life. It's literally a diary that records every single change, every commit, every rollback. If the power goes out, if a server crashes, the system can just read this log and restore itself perfectly to the last correct state. No committed transaction is ever truly lost.
So the real takeaway here is that every single time you click buy, there's this silent, invisible, high-stakes process happening behind the scenes, all governed by the rules of ACID. These rules are the bedrock of trust for our entire digital world, which leads to a really interesting question for the future, right? As new technologies like blockchain and certain types of databases come along, some of them are choosing to bend or even break these rules, all in the name of speed or scale. So it makes you wonder, what happens to our data when its invisible guardians are told to look the other way?